Hi everyone, in this video I'm going to present RetroWrite, a static binary writing framework with a focus on fuzzing and sanitization. This work was done in collaboration with colleagues at Purdue, Nathan Burrow, Professor Dongyan Zhu, and Professor Matthew Spire. Before we talk about binary rewriting framework for fuzzing, it is important to understand what fuzzing is and the major components involved in the fuzzing workflow. At a high level, fuzzing is a method of randomized testing where inputs are generated at random to an application under test. The application's execution is then monitored for abnormal behavior, such as unexpected termination, program crashes, or excessive resource utilization. When such unexpected behavior occurs, the input along with some additional debugging information is saved and reported to developer for further analysis. One of the ways to improve the effectiveness of such a technique is to improve the generation of inputs, and this is precisely what coverage guide fuzzing does. Rather than generating inputs purely at random, the application at test is instrumented to collect program execution traces. Based on analysis of these traces, better inputs are generated by the fuzzer in the future fuzzing iterations. Next, to ensure that the bugs in the application do not fail silently but rather cause an observable effect, applications are instrumented with sanitizers. For example, one such popular sanitizer for detecting memory corruption bugs in software written in low-level languages is address sanitizer. Lastly, compilers play a pivotal role in the fuzzing workflow as both the instrumentation for coverage feedback and sanitizers are implemented as compiler passes in popular compilers such as LLVM or GCC. Now that we understand how fuzzing works with the source code, let's try to understand why these techniques cannot be directly applied to binary-only applications. First, there are no efficient mechanisms to gather feedback for binary-only applications. This means we are limited to either generating inputs at random or be limited in the number of inputs that we can explore per unit time. Next, there are no binary sanitizers to aid in fuzzing. This means that a fuzzing campaign may miss a large number of bugs as the applications fail silently. Lastly, the core problem is that there's no efficient mechanism to instrument binaries. Ideally, what we want is an instrumentation mechanism that is as close to compile-time instrumentation in terms of performance overhead as possible. And this is precisely what we aim to do with RetroWrite. So what do existing binary fuzzing tools do? Well, existing binary fuzzing tools rely on dynamic binary rewriting for instrumentation. But this is bad for an application such as fuzzing, as the high overhead means the lower number of inputs may be explored by unit time, making the fuzzing campaign very ineffective. For fuzzing, we want to maximize the instrumentation mechanism's capabilities along three axes. First, the instrumentation mechanism must scale to large real-world applications so that we can fuzz the applications that we care about. Next, performance overhead due to instrumentation mechanism itself must be negligible. And lastly, the instrumentation mechanism must be flexible enough to support heavyweight source-like transformations. Dynamic binary writing tools such as Spin and DynamoRio are scalable to real-world applications, such as commercial browsers, but have a very high overhead, making them unsuitable for fuzzing. Moving to static rewriting approaches, trampoline-based approaches are scalable but have a high overhead due to the need to insert a control flow instruction for every instrumentation site. For an application such as fuzzing and sanitization, the number of instrumentation site scales with the number of memory accesses, and so this becomes unfeasible very quickly. More recently, reassemblable assembly-based approaches are promising as they have very low overhead and extremely flexible in the transformations that they allow. However, existing work rely on a combination of heuristic, static, and symbolic analysis that make them infeasible for larger real-world applications. In this work, we developed RetroWrite, which is a reassemblable assembly-based approach that maintains the performance and flexibility benefits while eliminating the need for heavyweight static and symbolic analysis. This enables RetroWrite to scale to large real-world applications. So what are the challenges in rewriting binaries? Well, binaries lack abstractions and have a very rigid structure due to hard-coded offsets. Consider this code snippet, for example, where the jump instruction has a hard-coded offset that points to the jump target, the move instruction. If we were to simply insert new code, This breaks functionality as the jump no longer points to the intended target and breaks binary semantics. One way to solve this problem is to identify all such pointers in the binary and readjust them to point to the correct location after the instrumentation. This is termed as symbolization by prior work and forms the crux of reassembly-based approaches. So what's the problem with identifying all pointers and rerouting them to the correct locations? The main problem is that binaries lack type information that enables the distinction between references and scalars. Consider, for example, this move instruction that stores a constant value into a memory location. Without further analysis, it is impossible to say if the constant is a reference, for example, storing a function pointer to a local variable, or simply a scalar assigned to a local variable. Misidentification of scalar versus reference breaks functionality in the binary, and in general, disambiguate between scalars and references is an undecidable problem. Existing solutions rely on a combination of heuristics, static and symbolic analysis to disambiguate between pointers and references. In this work, we developed RetroWrite, the first principled static binary writing framework for position-independent code. The key insight is that position-independent code is widespread for executive benefits, and we can simply reuse the relocation information embedded by the compiler to rewrite the binaries safely, without the need for any heuristics. Next, to aid in fuzzing, we developed AFL RetroWrite as a more performant alternative to AFL QEMU for fuzzing binary-only applications. Lastly, to detect more bugs, we developed binary-only address sanitizer ASAN RetroWrite, which outperforms other binary-only alternatives, such as Valgrind and Memcheck, in terms of both performance and bug detection rate. Next, we will dive into each of these three components individually and in more detail, starting with RetroWrite. RetroWrite is a binary writing framework that takes as input a binary application. The first stage in the pipeline is pre-processing, which includes parsing the binary format, disassembly, function identification, and a conservative CSG construction. Next, the symbolization procedure is invoked to find out pointers in a binary and convert them into assembly labels. The output from this stage is reassembled assembly that resembles compile-generated assembly files and may be freely modified by any of the instrumentation passes or other off-the-shelf tools. RetroWrite also provides an API that allows instrumentation passes to be implemented, and the generated reassembly may be instrumented directly within the framework. Lastly, the instrumentation is passed through a register allocation and optimization phase, after which a new binary may be generated using any off-the-shelf assembler. The key phase in this pipeline is the symbolization procedure that generates a reassemblable assembly. The first key point is that RetroWrite targets position-independent executables. As position-independent executables may be loaded at any offset in memory, the text section cannot have any hardcoded constant values that are references, simply because the addresses are not known at compile time. Rather, references are always relative to the program counter, or RRP relative. Going back to the example from one of the previous slides, if the constant value were a reference, it would be relative to the instruction pointer, otherwise it would simply be a scalar. Therefore, this reduces the problem of identifying scalars as references to either seeing if the operand is relative to the instruction pointer or simply a hard-coded constant. Now, let's take a look at symbolizing an example with the following code snippet. RetroWrite symbolization happens in roughly three stages. First, PC-relative control flow instructions are identified and their operands are changed to assembler labels, defining the labels of the offsets that they must point to. Next, RP-relative operands are converted to assembler labels as well. Lastly, using data relocations, all pointers in the data sections are converted into labels. At this point, we have reassemblable assembly that may be freely modified by the instrumentation passes and other off-the-shelf tools. Now that we have reassembled assembly, let's dive into the first instrumentation pass, AFL RetroWrite for coverage-guided instrumentation. AFL is a popular fuzzer that has been successful in finding bugs in the wild and has been a hot topic in the research community as well. To collect feedback, AFL measures edge coverage by maintaining in memory a bitmap of visited basic blocks during a program execution. All basic blocks are then instrumented to update this bitmap. While this could certainly be implemented with RetroWrite API, one of the key features of RetroWrite is its composability with existing tools. As the reassemblable assembly generated by RetroWrite is identical to compiler-generated assembly file, AFL GCC and AFL Clang, which operate on these, work out of the box with RetroWrite. This effectively means that we've repurposed the tool that instruments source code to work with binaries automatically. Look at performance. We evaluate AFL RetroWrite on real-world applications and benchmarks and compared against source-based solutions, AFL GCC and AFL Clang Pass, and against other binary-only tools such as AFL QEMU. AFL RetroWrite is about 4.5 times faster than AFL QEMU, which is the default binary-only solution shipped with AFL. Comparing to source code solutions, AFL RetroWrite is identical in performance. This means that we can collect coverage feedback for binary applications at the same cost as compile time instrumentation. In terms of bug detection rate, AFL RetroWrite on average finds just as many bugs as source code instrumentation. However, the binary-only QEMU is unable to find any bugs except for one on a single run of unique. This is primarily due to AFL QEMU being too slow and hence not exploring enough of the state space in a given time budget. The key takeaway here is that we can now parse binary applications with the same effectiveness as source-based instrumentation and recompilation. Now we move to the last piece of the fuzzing workflow, ASN RetroWrite, which is our binary-only address sanitizer. ASN RetroWrite is a binary-only port of the popular address sanitizer pass implemented in compilers such as LLVM and GCC. ASN has been extremely effective in finding memory corruption bugs in software written in unsafe languages such as C and C++. ASN RetroWrite uses RetroWrite API to identify two kinds of instrumentation sites. One, every memory access instruction is instrumented to check if the access is within an allocated region. If the access is not within the bounds of any scene allocation, the application is simply terminated and a detailed backtrace is provided for debugging purposes. Next, every memory allocation site is instrumented to track the allocated bytes. The specific instrumentation depends on the region in which the memory object is allocated in. For the heap, calls on memory allocators such as malloc are intercepted to allocate a larger object with some padding. Here, the blue region denotes the memory object that's allocated, and the red regions are the padding known as red zones that catch any overflowing accesses of this memory object and terminate the application. On the stack, this is a little trickier as allocations and deallocations are implicit in the functions prolog and epilogue. RetroWrite treats the entire stack frame as a single object and adds one red zone per stack frame. Rather than instrumenting every stack frame, RetroWrite reuses the fact that compilers add in a stack canary when its conservative overflow analysis cannot prove that the current stack frame is safe. That is, it does not overflow. RetroWrite and repurposes the stack slot allocated for the canary for the red zone. This improves performance as ASN RetroWrite does not need to instrument every stack frame that can never overflow. Lastly, for the globals, RetroWrite does not do any instrumentation. This requires identification of global boundaries, which is an undecidable problem in general, and we refer to readers to the paper for more details. What this means is that compared to source-based solutions, RetroWrite is and may miss a fixed number of overflows within the global regions. However, we observe that such overflows are very rare in practice. So how fast is ASN RetroWrite? In an evaluation on SpecCP 2006, ASN RetroWrite is about 3 times faster than Vagrant memcheck, which is a state-of-the-art binary-only memory checker. RetroWrite is still slower than source-based address sanitizer, and this is primarily due to the more sophisticated analysis and optimizations that compilers can perform at the source code level. Not only is ASN RetroWrite faster, but also detects more bugs than Vagrant on our benchmarks. A more detailed qualitative and quantitative analysis of our bugs found by the three systems can be found in our paper, and we encourage you to read it. To conclude, we developed RetroWrite, a sound heuristic-free framework for rewriting position-independent code. We developed two passes in RetroWrite, AFL RetroWrite for coverage guide fuzzing, and ASN RetroWrite, a binary memory checker. Through our evaluation, we show that AFL RetroWrite and ASN RetroWrite are viable alternatives to their source-based counterparts when source code is unavailable or recompilation is simply not possible. RetroWrite is open source in our GitHub link on the slide, and we encourage you to give it a try. Thanks, and we look forward to hearing your questions in our Q&A session.